Hi everyone, welcome back to the garage. Today we're going to be discussing mass airflow sensors, or airflow sensing in general. I'm recording this video a little bit earlier than usual, so you might hear my kids running around outside screaming like banshees, so don't be alarmed. They're probably not getting hurt. Okay, so mass airflow sensors are probably the airflow sensors you're most familiar with. That's what we use on modern cars. But we're going to start by talking about airflow sensing as a whole, kind of why it's necessary and how it used to be accomplished. So it may seem like kind of an obvious thing, but the reason we sense airflow in an engine management system is so that we can produce a correct air-fuel ratio, or an AF ratio. Okay. And as you may have remembered from previous videos, somewhere around 14.7 parts of air to 1 part of fuel is considered ideal. And that ratio is based off of mass, okay, not volume. So it wouldn't be like 14.7 gallons of air to 1 gallon of fuel. It would be 14.7 pounds of air to 1 pound of fuel. Excuse me. Sorry about that. So, again, there's that mass word, which might explain why we call it a mass airflow sensor, but we haven't always had mass airflow sensors. We've had to use some different technology over the years. So, I've already taken and put that carburetor away that was on my bench. Obviously, a carburetor didn't require an airflow sensor. A carburetor was completely based off of airflow. So, as air would flow through the carburetor, fuel would get mixed with the engine in somewhat proper proportion. Worked great as long as that carburetor was set at the elevation you were operating the car at and the temperature you were operating the car at. So come winter, you would have to readjust your carburetor a little bit, come summer, etc. So when we went to fuel injection, we eliminated some of these problems, but we haven't always kind of gone about it the same way because we haven't always had the technology that we have now. So in one of our previous lessons, we mentioned that there's a sensor known as a map sensor. And you might remember a map is a manifold absolute pressure sensor versus a mass airflow sensor. Your vehicle may have both, or it may have one or the other. It doesn't necessarily need both. Prior to mass airflow technology being reliable and affordable, we used to rely a lot on map technology, and there are still some cars that use map sensors. I'm sure there are not too many left, but there's definitely some out there. And a lot of older cars running around use map sensors rather than mass airflow. So the whole concept with a map sensor is we're going to look at the manifold vacuum, or the manifold pressure, more accurate term, and that's the pressure after the throttle body. There's my throttle. So we're looking at the pressure in here. We're going to measure what the pressure is in there, and that's a fairly adequate way of figuring out what load the engine is under and how much air is being consumed by that engine, so we can calculate how much fuel to deliver. However, it doesn't really tolerate air leaks very well, vacuum leaks, and it doesn't tolerate engine modifications very well. So if you were to go ahead and put some different aftermarket camshafts in here, this system would be thrown all out of whack until you got in and hacked the computer and reprogrammed it. A mass airflow system, on the other hand, actually measures the air coming in after your air filter. So here's my air filter housing, my air cleaner box. Inside there would be an air cleaner element nestled down in there. And this would be my mass airflow sensor. So this is going to actually directly measure all the air coming in to the engine rather than a vehicle with a map sensor that's calculating the air coming into the engine. So if you're calculating the airflow coming into the engine, by the way, That's known as a speed density system. Because we're going to look at the speed of the engine, and we're going to measure the density of the air, and we're going to basically do some really fast math. The computer is, after all, just a really big calculator. And we're going to calculate how much air the engine actually took in, so we know how much fuel to deliver. So this calculates fuel demand. And it works pretty well. But I think most would agree that a mass airflow system works even better. So if you have a mass airflow sensor, we just call it a mass airflow system rather than a speed density system. So again, to try to achieve this 14.7:1 air-fuel ratio, we can either use a map sensor and do some math in the computer, and we call that speed density, or we can measure the air coming in. So let's talk about how we actually measure air coming in the engine rather than calculating it. So one of the first systems that actually measured air coming into the engine, it didn't measure air mass, but it did measure air volume, and it was what Bosch called KJettronic. So as the Ronic would kind of indicate, there's some electronics going on in here. Jet, well, they applied the jet, maybe they meant like a jet of fuel being injected, but these, the Jettronic was sort of their name for all of their fuel injection systems for a number of years. They had all different generations, D-Jettronic, K-Jettronic, L-Jettronic, etc. So the K-Jettronic came out somewhere back in the early 70s, and it was used all the way up into the 90s, believe it or not. And it had this big ugly thing either on the air cleaner housing or on top of your engine. So this is actually the lid to the air cleaner. So your air filter would be underneath this thing. All the air would be coming in from the bottom. It would come up in here. And it would have to push its way through this measuring plate right here on its way to the engine. There'd be a big rubber boot right here that would lead to a tube that went to the throttle body. So all the air coming into the engine had to come through this metering plate. So metering, another term for measuring. This measuring plate with this flap would move a control valve inside this mechanism right here, known as a fuel distributor. You might notice it kind of looks like an ignition distributor, but instead of high voltage spark plug wires coming out, it's got braided steel hoses coming out. Okay, they're actually plastic inside and covered with braided steel. So these hoses went to the fuel injectors, and these were mechanical fuel injectors. These things don't have any electrical components to them whatsoever. When the pressure reaches a certain level, they spray. And this system was known as a continuous injection system, or CIS, because basically these sprayed a metered amount of fuel at all times. Basically, the whole time the engine's running, this is spraying. Doesn't matter if the intake valve in this port is open or closed, there's fuel spraying. And as inefficient as that sounds, when these are tuned properly, they actually work really, really well. I'll put that down for a moment. So, this used a fuel distributor and a metering plate, or a flap. So this measured air volume. So air volume is good. If we know the volume of air coming in, that's good. But what we don't know is the air density. We have to measure that in some other way. Because as you know, hot air is less dense than cold air, so it's going to contain less oxygen. As you go to different elevations, if you were to drive up to a higher elevation, up Mount Washington or up to Colorado or something like that, the air is going to be less dense due to the elevation. So this is pretty good, but there's some other sensors that are needed to make it work properly. So there was another component in that system that compensated for air density changes. So it worked pretty well. And again, just one more note here. This was a CIS, or continuous injection system. All right. Here in the US, we typically just called it CIS. And it worked pretty well for a number of years. Something like a 1993 Porsche was the last vehicle to come with it. I couldn't even begin to tell you what the first one is, or was. and lots and lots and lots of European vehicles came with this for many, many years. So worked all right, but it's a mechanical system. It's not actually measuring air mass, but it was really probably the first airflow sensor installed in a fuel injection system. So fast forward a bit, and Bosch came up with another version of Jettronic, and if I remember correctly, it was L, but I could be wrong. That was a little more electronic. It wasn't a continuous injection system. It had a computer, had some electronic fuel injectors, and it had what was kind of a breakthrough at the time, something known as a VAF. Some people say this stands for a volume airflow sensor, but it's actually a vane airflow sensor. And once again, this is only going to measure volume, not mass. And this sensor right here, which you're not going to see on anything remotely modern, is again built into the air cleaner lid. This one actually came off of a Toyota, despite Bosch being a European company, a German company. They licensed their technology to a lot of different manufacturers. So we take this air cleaner housing off. This is our vane airflow sensor. And basically, this is like a turnstile at the subway station for air. As the air came in from the air cleaner, it had to push its way through a little spring-loaded flap. I'll bring this up close so you can see what's going on in there. There's a little airflow flap. If I push it far enough, you can actually see through it. Okay, so again, it's kind of a mechanical-based sensor, although it is electronic. You can see there's a bunch of wires coming out up here. What we've been learning about lately, like TPSs and APPs, you might remember a potentiometer is the actual sensing element that's up inside here attached to that flap. And basically, air has to push its way in past the flap. Airflow moves the flap, and a potentiometer senses the position of that flap. So this works all right, but there's a few issues. One, it only measures the volume, not the mass. Two, as you've learned in previous lessons, a potentiometer is going to wear out. It's going to develop little dead spots where it doesn't make contact and little glitches in the signal. It has to be very carefully calibrated for the engine it's installed on. So if you were to take the mass airflow or the vane airflow sensor off of one engine and put it on another, the spring tension on that flap may not be the same. So it's not going to actually report the correct amount of airflow. This sensor is a restriction. So because the air has to push its way past this, it is actually a flow restriction. So it's got a few drawbacks. So measures volume, not mass. Has a potentiometer, so it's going to wear out. And it has to be finely calibrated, and it's restrictive. And as you know, a restriction is not good for making power. So three major drawbacks there. All right, hopefully no questions on that. If you do have questions, you're going to have to email them to me and I can answer them in a subsequent video. Okay, so moving on from that vane airflow sensor. That old, outdated, mechanical, potentiometer-based, non-mass measuring sensor. We're going to start talking about true MAFs, or mass airflow sensors, with an emphasis on the mass. So it's going to actually measure the mass of the air, the weight of the air coming in, so that we can very accurately report to the computer the airflow, and then therefore mix in the correct amount of fuel. So, check my time here. Oh yeah, plenty of time. A couple of ways of going about a true mass airflow sensor. One of the older technologies that's actually still in use is what we call a Hotwire, MAF. And it basically uses a heated wire, hence the name Hotwire, dipped down into the airflow stream that gets cooled off by the incoming air. So we're going to take a little hot filament, . you think it looks like a resistor, that's on purpose, because it basically is. And that's going to be in the airflow stream inside this sensor. And there'll be some electronics up on top. As the air comes in here, I don't know where I lost my blue marker to. I guess we'll go with green. As the air comes through, it's going to cool down that hot wire. The electronics in the mass airflow sensor try to maintain the temperature of that wire at a constant level. And the amount of current it takes to maintain the temperature of that wire is what produces our signal to our computer, to our PCM. So, air cools the hot wire. The electronics vary the current to maintain the temperature. And then a signal gets sent to your PCM. Okay, so I have here a older Ford Hotwire mass airflow sensor. The metal body you see has an opening for the air to flow through. There's a screen on the front here. If anybody ever tells you that that screen is a restriction and you should take it out for more power, don't believe them. It's actually there to straighten out the airflow and make the airflow more smoothly across the hot wire. It doesn't really restrict anything, but it does increase the accuracy of the sensor. These are tamper-proof Torx screws, T20s. They don't want you to take this apart, but we have the tools, so we're going to. So when we take this off, there are a couple of tiny little filaments right here. I'm going to zoom in on here. And if they look pretty small, that's because they are. So these little filaments right here, one of them gets hot and one of them stays cool. So the cool wire, or the cold wire, is basically a reference for the electronics that are built in here. And the hot wire, and I couldn't tell you which one is which, the hot wire is the one that gets cooled down by the incoming air and actually does the measuring. Now, one problem with this type of sensor is dirt and contamination that builds up on those little wires. And one thing that's notorious for contaminating them would be these aftermarket air filters that people put in. This is a cotton gauze air filter, and cotton makes a pretty good filter, but it does a much better job of catching fine dust when it's oily. So these filters get oiled, hence the color. And if you over oil them, because again, if a little oil, like the instructions say, must be good, lots of it must be better. When oil actually gets picked up by the airflow and coats that hot wire, it will contaminate the airflow sensor. If you've ever heard of somebody talking about cleaning a mass airflow sensor, this is the type that tends to get dirty, and cleaning it sometimes will restore its operation, although none of the manufacturers actually recommend you cleaning their airflow sensors because they have no control over how careful you are or what chemicals you use. So if you find a problem with a mass airflow sensor, they pretty much prefer you to just replace the sensor with a new one. Okay, so these sensors come in different sizes. This is a later model Ford sensor. You might notice that the airflow opening is much bigger and the design is a little bit different. The one on my left here is like a 59, 60 millimeter sensor, something like that, and this one over here is an 80 millimeter sensor. So if anybody ever gives you the idea to change out your mass airflow sensor for a bigger one, like it's going to make more power, keep in mind, if you're only breathing through a 65 millimeter throttle body, an 80 millimeter mass airflow sensor is really not necessary. And what it's also going to do is it's going to upset the calibration of the computer if you don't go in and do some reprogramming. So the computer knows how big the stock airflow sensor is. If you put a bigger one on there and change nothing else, the flow across that little hot wire is probably not going to be quite as vigorous, and it's not going to report the correct signal. So you're going to have a calibration problem, which is going to give you a fuel trim problem. And we'll talk about fuel trim a little more on Friday when we get into our fuel injection and pulse width lesson. So fuel trim, just heads up, is basically the adjustment the computer makes to your air-fuel ratio, and it's basic programming. It either adds a little fuel or takes away a little fuel. Okay, so Much better sensor than our old vane airflow sensors because it's actually measuring the air mass. And they do work pretty well. Again, they can get contaminated, but they're very popular. They're still out there today, still in use. There's a variant of this sensing technology known as a hot film. So rather than a little filament like a light bulb filament, it's a little thin film that the air flows across. And there's some pros and cons to each. Bosch claims the film is a better technology. It stays cleaner. I can't comment on that. I really don't know. Okay, so that is our Hotwire mass airflow. Another strange design that you might see is something known as a Karman Vortex sensor. I'm going to try to describe this briefly for a couple of reasons. One, I don't want this video to take so long that I have to make a second part before my phone stops recording. And two, it's really not critical that you understand every little bit of the workings of this Karman Vortex. It's just more important that you kind of understand what it's there for and sort of basically how it works. So if this is the sensor itself, and the air is going to come flowing through here, first thing it's going to encounter is a screen. That screen is there to straighten out the air. Then what it's going to encounter is a little triangular rod and a rectangle right behind that. And that's going to make the air swirl. As the air comes in here, it's going to swirl or make vortices, the plural of vortexes. So these little swirling vortices are going to come through here. And the next thing we're going to encounter a little tiny speaker and a little tiny microphone. So they have a fancy name for it. They call it a transducer. And the microphone is there. It's a little pickup. And basically, there's going to be some ultrasonic sound waves being transmitted from the transducer or the speaker to the microphone. And these vortices are going to disrupt those sound waves. So if you were ever a kid and talked into a box fan and made your voice sound all kind of crazy, that's sort of what's going on here. We're disrupting the sound waves, and the electronics in this sensor are going to use that amount of disruption to come up with a signal. So air vortices, plural of vortexes, disturb sound waves. Actually an extremely accurate method of sensing airflow. There's also industrial uses for sensors like this. They use similar sensors for measuring water flow in pipes, so like water distribution systems and chemical distribution systems. There's all kinds of uses for this technology. In cars, we pretty much only use it for measuring airflow, and the only ones that are really doing that a lot are Mitsubishi. Mitsubishi was big into this sensor. Check my time here, make sure I'm not talking to a dead video. Nope, doing pretty good. Okay, so whether you have a Karman Vortex on a Mitsubishi or you have a Hotwire mass air on pretty much anything else, or a hot film, they're both there for the same reason. They're there to measure the mass of the air, your air mass, which is going to be better than volume, once again, because volume is not really telling us what we need to know. We can calculate the mass if we know the volume, but if we're going to do calculations, we might as well run one of these little map sensors like we learned about in another lesson. So, a couple things just to sort of sum up here. Hotwire sensors are sensitive to contamination. Ooh, I can't spell today. Sensitive. And if they get contaminated, they're going to report a false signal. The other thing that will report a false signal is if you have an air leak in this duct. So if this is your airflow sensor, no matter what kind it is, whether it's an old vane sensor or a vortex or a hot wire, if you've got air sneaking in after the sensor, that's known as unmetered air. Unmetered air. What it's going to cause is a fuel trim problem. And maybe even a code if it's severe. You'll get a trouble code. So system too rich, system too lean. In this case, you'd be getting system too lean codes, and your fuel trim would be pegged positive, meaning it's adding fuel to make up for that air that's sneaking in somewhere else. Another way to get a similar problem, people don't necessarily understand what they're doing sometimes. They add what's known as a blow-off valve, or a BOV. To a turbocharged car, because they like that sound when they let off the throttle. Well, that sound is caused by this blow-off valve diverting that air to the atmosphere. Well, basically, if that car is using a mass airflow sensor, all that air was measured on its way in through the air cleaner, and it's been counted, it's been tallied. The computer knows that air is in the system. It may not have gotten into the engine yet, but it's in the system. It's in the piping, it's in the intercooler, it's in the turbo, it's on the way to the intake manifold. When you blow that air off to the atmosphere, you're again making a fuel trim error, because now we're going to add fuel for air that's no longer there. So now we're going to get a rich issue. So, blow-off valves where they don't belong, unmetered air from air leaks. So we'll just put that there, leaks. And the wrong sensor in general, a mismatched sensor. Which, as we said, is calibrated to the engine.